Welcome back, everyone. In this video, I want to introduce ourselves to the concept of a logarithm. So logarithms are just inverses of exponential functions, and exponential functions and exponential equations model all kinds of real-life situations, and it's going to be really important to be able to solve those exponential equations. Logarithms are going to be our tool for doing just that. So the first note I want to make about logarithms is that they are inverses of exponential functions. So how exactly does this inverse relationship work for an exponential function in a logarithm? Let's go ahead and start by looking at an exponential equation. So normally for an exponential function, we take our input x, raise it to the power of some base b, and out pops some number like y or a. And so the idea is in goes x to our function b to the power of x, and out pops a number a. Well, a logarithm is an inverse of an exponential function, and it is simply going to reverse this process. So the output of our exponential becomes the input of our logarithm, and the input of an exponential becomes the output of our logarithm. So we do use a new notation for logarithms. Let me go ahead and show you what that looks like. We're going to write the following equation in an equivalent way as log base b of a is equal to x. So these two equations I've written here are 100% totally equivalent equations. They mean the exact same thing. They're just expressed in two different formats. This is what we call the exponential form of the equation. While over here, we read this as log base b of a is equal to x. That is the logarithmic form of the equation. And I've probably already done it a couple times, but we're going to get used to just using the word log instead of logarithm or logarithmic, just to save some space and time. So it definitely takes a bit of time and experience to get used to this logarithmic form of the equation, or just this logarithmic notation in general. One important thing to keep in mind that'll help us kind of make sense of this logarithmic notation is what comes out of a logarithm is always or can always be interpreted as an exponent. So if you're ever looking at a logarithm and confused about what it's representing or what it's trying to do, it's trying to tell us an exponent, or what comes out of a logarithm is always an exponent. In more detail, what comes out of a logarithm is the exponent or the power we have to raise the base of the logarithm to get the exponential value inside of our logarithm. And that's what this equation is really trying to communicate to us. B to the power of x is equal to a is the same thing as log base b of a being equal to x. What comes out of our logarithm is the power we have to raise our base to get the number inside. So b to the power of x should be equal to a. That's exactly what our exponential form of the equation is saying. All right, so let's go ahead and do an exercise looking at different equations and switching their forms. So if they start in an exponential form, we want to switch that to a logarithmic form. And if they start in a logarithmic form, let's go ahead and rewrite that in the exponential form. The point of this exercise is just to get us used to and comfortable with this notation for logarithms. So let's go ahead and start with this exponential equation. 2 to the power of 3 is equal to 8. We know that's true based off our multiplication tables and what we know about powers of 2. But what does this look like in its logarithmic form? Well, the base of our logarithm is always going to correspond to the base of the exponential. So we can start off with that. We're working with a log base 2 because the base of our exponential is 2. Then what goes inside of a logarithm is what comes out of the exponential. So that's going to be 8. That's our exponential value. And then what our logarithm is equal to, or what comes out of the logarithm, is the power or the exponent. The exponent we have to raise the base to get the number inside. And as we see from the exponential form, that power or that number is 3. So log base 2 of 8 being equal to 3 is 100% the same thing as saying 2 to the power of 3 is equal to 8. All right, let's go ahead and look at another exponential equation. This time let's do 3 to the power of 2 is equal to 9. How do we convert this exponential equation or statement into its logarithmic form? Well, just using the same process before, we start with the base of the logarithm. That's going to be the base of our exponential. And so that is 3 in this example. Then what goes inside of our logarithm is what comes out of our exponential. And so that's going to be this number 9. And then what comes out of the logarithm, or what the logarithm is equal to, is always an exponent or a power. It's the power we have to raise the base to get 9. And we have to raise 3 to the power of 2 to get 9. So 3 squared being equal to 9 is equivalent to saying log base 3 of 9 is equal to 2. Let's go ahead and look at one more example of converting exponential equations to logarithmic equations before we reverse the process. So here, we're starting with 4 to the power of negative 1 is equivalent or equal to 1 over 4. And so what is the logarithmic form of this equation going to look like? The base of our logarithm is the base of our exponent. So here we're going to be dealing with a log base 4. what goes inside of our logarithm is what comes out of our exponential. So that's 1/4. And then what our logarithm is equal to is the power we have to raise the base 4 to get 1/4, and that's -1. So hopefully from these first 3 examples, we're building up a little bit of comfort converting from exponential to logarithmic form. Now let's try to go the other way from logarithmic form to exponential form. All right, so let's go ahead and start with this logarithmic expression. We have log base 2 of 16. Well, before we switch forms, let's figure out what this is equal to. So what is going to come out of this logarithm is an exponent or a power. It's the power we have to raise the base to get the number inside. So this is equivalent to asking what power do we have to raise 2 to get 16? Well, 2 to the first is 2, 2 squared is 4, 2 cubed is 8, and 2 to the power of 4 is 16. So 2 to the power of 4 is 16 is the key there. We have to raise 2 to the power of 4 to get 16. So log base 2 of 16 is equal to 4. And we basically said it like 3 or 4 times there, but the exponential form of this logarithmic equation is 2 to the power of 4 is equal to 16. 2 is the base of our logarithm. We raise that to the power of 4, or what our logarithm is equal to, and that needs to equal the number inside of our logarithm, and 2 to the 4 is equal to 16. All right, let's look at another example or two. Up next, I got log base 25 of 5. And so log base 25 of 5, we can think through this by thinking, what power do we have to raise 25 to get 5 as the output? And well, if we take the square root of 25, we get 5. So we have to remember that a square root is the same as a fractional or rational exponent of 1/2. So log base 25 of 5 is going to be equal to 1/2. And we can verify that in a more familiar way by converting this logarithmic equation to its exponential form. The base of our logarithm becomes the base of our exponential. What comes out of our logarithm, or what our logarithm is equal to, is the exponent or power. And then 25 to that power, or the base to that power, is what should be inside of our logarithm. And 25 to the 1/2, or the square root of 25, is equal to 5. All right, let's look at one more just for fun. So now we're looking at log base 6 of 1 over 36. What is that going to be equal to? Well, what power do we have to raise 6 to get 1 over 36? That one might be a little bit hard to think through, so maybe we can actually start by thinking, what power do we have to raise 6 to get 1 over 36? Well, we know 36 is the same as 6 to the power of 2, and we have 1 over 36, though not 36. So if we can write this in the numerator, I think it'll be more easy to find that value of x. And 1 over 6 squared is the same as 6 to the -2, although we wouldn't say that's in the most simplified form. But writing this unsimplified form is useful because now we can see, well, if the bases are the same and they're equal, that means the exponents need to be the same. That means x needs to be equal to -2. So this little scratch work off to the side was just helping us figure out log base 6 of 1 over 36 is equal to -2. And we can verify that by converting it to the exponential form and evaluating that exponential form. 6 to the power of -2 is equal to 1 over 36. So in this example, the base of our logarithms were the numbers 2, 25, and 6. Any number that works as the base of an exponential will also work as the base of a logarithm. And so that's all the numbers between 0 and 1 and all the numbers bigger than 1. We cannot have negative numbers or 1 be a base for a logarithm. And really for the same reasons, we can't have that be a base for an exponential function. With that being said, though, there are 2 bases that are used most often for logarithms. That is log base 10 and log base e. And so these 2 logarithms are denoted in slightly different ways where we don't actually write the base of the logarithm clearly in this function notation. So log base 10 of x you will see just as log of x. So if you don't see a subscript there in the spot for the base of the logarithm, you can safely assume that it is a base 10 logarithm, and the name that is given to this logarithm is the common log. Well, down here, when we have log base e of x, that is referred to as the natural log of x, and it's denoted using ln of x. And if you haven't seen this number e before, that's okay. You'll definitely be running into it a lot coming up soon. E is an irrational number, like pi. E has a decimal approximation of about 2.718281828, and then just repeats forever with no discernible pattern. It's an irrational number like pi, but it has all kinds of important uses and applications in math and sciences. It shows up just as often, if not more often, than pi does. So I think the common log is an important logarithm and shows up all the time because, well, 10 is the base of our entire number system, so it kind of makes sense to work with base 10 for a logarithm as well if we use base 10 for all of our numbers. But using e as a base seems a little unnatural, kind of funny given the name that it's the natural log, but it ends up being really, really beneficial, and this is the best kind of logarithm to use. Unfortunately, we can't give a good motivation for why this is the best logarithm to use until we get to calculus. So trust me, and just take my word for it for now at least, that the natural log is the best logarithm. It has kind of a bunch of nice properties that we can't learn about, just not yet at least.